In this video, we'll discuss how we can use what is called an ICE chart to harness the predictive power of the equilibrium constant. What ICE charts do is that they map the flow of the change in initial concentrations of a reactant, how that changes as a loss for the reactant and as a gain for the product, until finally an equilibrium is reached. From there, we can take those equilibrium algebraic expressions and manipulate them into the KEQ formula to come out with what is essentially a quadratic equation that we can resolve with the quadratic formula and determine how much of our product of our reactant will remain and how much of our product will be produced once the system has reached equilibrium under a set of conditions. So to back up here a bit, if we have a hypothetical reaction between dinitrogen tetroxide and to make nitrogen dioxide, we have derived experimentally that our KEQ is 5.76 times 10 to the negative third. We can take whatever concentrations of our reactant that we want, as long as we're remaining at the same temperature pressure conditions, and figure out how much of that concentration will be left over and how much of our product will be produced. So the way that an ICE chart flows is that we start off with I, the initial concentration of our two chemical species. Of course, at this point, the concentration of the product is going to be zero. At least in the cases that we'll be looking at this semester, it will always be so. We'll start off with a given known concentration of our reactant or reactants. In this case, we only have one reactant, dinitrogen tetroxide. And this is a 0.1 molar solution. So we let the reaction begin. And so we will measure the amount that has been lost in the change as X. So stoichiometrically, how much X has been lost, thus the negative symbol here, we assume that we have a countervailing gain on the product side multiplied by its stoichiometric coefficient. So this is to remind us that this is a form of stoichiometric manipulation. From there, we reach eventually endpoint or equilibrium, or our final state, so to speak, and that is our E in our ICE chart. And so logically, we have this expressed as what we started off with minus whatever was lost in the reaction. That basically is our measurement of our change in our reactant. We have a corresponding gain on the product side. So basically, the C for our product is the same as our E, just conventionally that plus symbol gets dropped. From there, we can now plug this in to our KEQ expression of products over reactants. So here, if we have our KEQ, it will thus equal products with our coefficients expressed here, which is 2 in this case, over reactants. That's an implied 1. We can plug in the values that we've derived in the E part of our ICE chart thus. So nitrogen dioxide, of course, we determined it will be double however much was lost by E, and we square that because it is our coefficient is 2. On the other hand, on the reactant side, which is the denominator of our equation here, we put in the 1 minus X, denoting that we had a set concentration 0.1 molar and we lost a stoichiometric amount. So thus, we can eventually boil this down to this type of an equation. I've pretty much set it out here as this expression, but for the sake of people who have trouble with the implied cross multiplying and dividing, we can always put in an imaginary 1, and you can see how this rearranges into this expression. So basically 4x2 equals 5.76 times 10 to the negative third power times this 0.1 minus x expression. We distribute this out to these two values, and thus we have this equation. And if we want to solve this quadratically, we do what we typically do in algebra, is set everything on the other side so the equation is set to 0. So thus, moving this value over, that's positive here, it will be negative there. It's negative on this side, this one is, it will become positive on that side. So now we have a quadratic equation. And from here, we can determine our A, B, and C that can be plugged into the quadratic. A, in this case, is 4. B, in this case, is 5.76 times 10 to the negative third. And then C is negative 5.6 times 10 to the negative fourth. And I put them here. So if we take these values and plug them into the quadratic equation, we will yield two answers, because this expression right here in the quadratic requires us that we do it 2 times, one time for where this square rooted expression is a positive value, and a second time where the square rooted expression is a negative value. Actually, I reverse that here, but you get the idea. Then it's time to evaluate which actual expression holds. This expression does not work, because if we actually plugged it into these coefficients, we would get a positive concentration here, but 2 times any negative value will be a negative concentration. You cannot have a negative concentration of something that is illogical. So by default, answer 2 is our x. So now we can plug x into this expression of equilibrium for our reactants, and we determine that equilibrium, out of that 0.1 moles, we have 0.0887 moles remaining. And our gain, which is our E expression here for nitrogen dioxide, we multiply our x times 2, and we have produced at equilibrium 2.26 times 10 to the negative third power, or 0.00226. Thus, by using the ice chart, we can produce an algebraic expression that can be manipulated into a quadratic and be resolved and evaluated in a way that can tell us at the end of a reaction, if we have a known KEQ, how much of our reactant will be left over and how much of our product will be produced.